Swayam Prabha. Digital India. Educated India.
Good morning. Welcome to the third lecture of this week 6 of ongoing course on understanding and reducing greenhouse gas emissions, and we are looking specifically at the contribution of building design and construction towards emission and then towards reduction of scope 1 and 2 emissions here. In today's lecture, we are going to look at some advanced passive design measures. So, in the previous lecture, we had looked at the different types of passive design strategies specifically for heating as well as cooling. We are going to continue the same discussion further, and we are going to look at some advanced passive design strategies. Now, why do we call them advanced? Is because sometimes these passive design strategies, they require extra construction other than the building envelope which is going to be there. So, earlier what we had seen was we were looking more at design strategies and some construction strategies, but here we are looking at strategies which other than the building that is going to be constructed are going to be added on top of that, but will work passively only. So, that is why we are calling them advanced passive features. Some of them may also require a little bit of energy to be supplied to make them function well, which we will see in the lecture today. So, in this lecture we are going to look at some of the advanced passive design strategies such as thermal insulation, thermal mass, courtyard effect. We have seen courtyard as a design element. We will look at the detail of it here, and then evaporative cooling, different types of versions of evaporative cooling as in down draught cooling or roof sprays are all different types of evaporative cooling, and earth air tunnels. So, let us begin with the advanced passive strategies. So, the first one is thermal insulation. Now, if you look at the mandate in terms of codes, energy codes in our country, we are recommending thermal insulation. Now, what does thermal insulation do? It stops the heat from being transferred from the hotter surface to the cooler surface. So, or the environment. So, what we are seeing here, for example, if you look at this one here, so what we see here is this is the same building, and in one part of it, it is uninsulated, there is no insulation. Now, insulation primarily is a material which has very low conductivity. So, it will not conduct the heat from one side to the other, or it will not allow the heat to pass through it. Now, if we have added insulation like as you can see here, then what will happen? The radiation is going to incident on this roof. Then if I take this roof slab as the section here, so when there is an incident radiation on this roof, which is when the sun is out there, plus we also have positive temperature if we have a higher temperature outside. So, this surface is going to receive heat through radiation as well as conduction, because there is a higher temperature. Now, this heat is going to be absorbed by the material. It will take time depending upon the specific heat and mass of this material. This material will take time to completely heat up. So, this surface will get heated up fast, and gradually the heat will be percolated, and then this heat will be re-emitted from the other side. Not just the other side, this heat is also going to be re-emitted during the night time from this side. So, from both the sides it is going to be emitted equally. Now, imagine if we have an insulation layer here. So, we add a barrier. Once we have added this barrier, so when the heat is trying to escape from this side, there is a barrier of a low conductivity material, and it will stop it from going to this side. So, this heat will ultimately have to escape to the outside. Now, this is required in case we are preferring cooling. So, it is in a warm climate and we want the interiors to remain at a cooler temperature. What if we are looking at cool temperatures, the cool conditions outside, and there is more heat inside? In that case, we want the heat to be brought inside, but during the night the reverse is not going to happen. So, in that case also we will have to insulate. Now, what we are going to do there is that again we will put the insulation, but this time to stop the heat from this side to be going to the other side, and the coolth from this side to be probably coming this side. So, that is what this thermal insulation is going to do. For this thermal insulation we have a lot of different materials, but all the materials, whether it be synthetic materials like polystyrene, or we could be using materials such as glass wool or rock wool, mineral wool, which have less density, which have a lot of air gaps in between, which act as insulators, plus they have very low conductivity due to all these reasons. And that is why this thermal insulation, the concept of it works, but it is always going to be an additional thing. We can also have thermal insulation with the help of air itself. So, in case we have a cavity wall, the air cavity in between also acts as insulation, but it is not as effective an insulation as the slightly more insulating material which have been industrially manufactured, but we also have to see the footprint. So, if we look at it in the long term, the overall emissions, so there we can also consider the choice of material, but we have the possibility of providing insulation using the air cavity, the air gap in construction. The next one is thermal mass. So, as I was just mentioning that if we have a roof slab or a wall, and then the heat is incident, the radiation is incident on this material, then this material absorbs heat and it passes it on inside. Now, the thickness of this material T and the specific heat and the heat capacity of this material will determine how much time will this material take to transfer the heat from here to here at a given starting surface temperature or the temperature of the body. So, if assuming that the body is at a cooled down state and is at an atmospheric temperature there, so then this body, if it is assumed to be a very thick stone wall like you would have seen in some of the forts in India. So, probably 1 meter or a 1.5 meter thick stone wall. If a lot of radiation is incident on that, even then the entire mass of the stone wall is not going to get heated up to a level where it becomes hotter than the indoor temperature and it starts to transmit inside. So, the transmission is only going to take place, the re-emission of that heat is only going to take place when the temperature here, the Ti, is higher than the temperature of this body, the Ts. So, it is only going to take, it is only going to happen in the case where, where Ts is higher than Ti. So, when the temperature of this body is higher, then it will start emitting to the indoor temperature, and that is what we are seeing. So, what we want to do in case we want to reduce this heat ingress or egress, and there is a lot of difference between the temperatures of indoor and outdoor, is we want to provide heavy thermal mass. There is a lot of mass. So, this mass itself acts as a balancer, a neutralizer. It will continue to take on more and more heat, but it will transmit very less towards inside, because what will happen that if it is a thick stone wall, assume it to be that, and there is radiation. So, it is passing, since it is so dense and thick and there is a lot of heat capacity, probably in a day heat is transferred only up till this and the rest of it remains at a normal temperature. Now, when the re-emission is going to happen, so then from this point the heat is going to be released further and there will be very little portion which will further be transmitted. Overall, more heat is going to be emitted again, re-emitted back outside, and that is how this thermal mass will work. Now, the time which is taken will create the time lag that we see. So, at the time when the outdoors are extremely hot and a lot of heat is being radiated onto the surface continues to absorb and absorb, and gradually it will continue to pass it on over time, maybe an entire 24-hour or 12-hour. Now, that is where we have to also design, because in our climate the night time is comfortable and outdoors can be used for sleeping and other activities. So, what we have planned traditionally is that this material will be provided sufficiently thick so as to provide us a time lag of almost 12 hours. So, during the daytime when it is extremely hot, say around noon time, it will continue to absorb and it will release late in the night, that is when the outdoors would have already become comfortable for human use. So, that is what thermal mass will do, it will give us a time lag. Sometimes it will not transmit the heat inside at all, it will continue to absorb and it will continue to absorb for an entire hot season and will release gradually when it is colder season to both the sides. So, that is also a possibility, that is what thermal mass does. But again we see here why we have put it in advanced passive strategies. This is a passive strategy only because it requires a lot of material consumption and extra efforts to only make the same wall, which otherwise we would be doing as a 9-inch thick brick wall, to make it some double the thickness or triple the thickness to achieve this effect. The third strategy which we are looking at here is cool roof. Now, cool roof is basically it is kind of a coating on the roof which will allow more and more heat, the radiation, to be reflected back, and whatever is emitted is also re-emitted back into the sky. So, what we are seeing here is, suppose we have a roof here, there are 3 ways, as I said, in which the transmission is going to take place. So, there is this radiation which is incident, this radiation is going to get absorbed into the material, half of this is again going to be re-emitted back to both the sides, and then there is conduction which is helping the temperature to get warmer because of the conduction also. Now, what we are trying to do here is, one, we have a reflective coating on the top. So, more and more of this heat is going to be reflected back and there is very small portion of it which is going to get absorbed. Now, so there is more reflection, so reflectivity is high here in such cool roofs, and whatever small amount is going to get absorbed, since it is going to get emitted both sides back, what we are making the material as is that more and more of this heat which is absorbed here, even the smaller amount, is going to be re-emitted back. That is how the cool roofs work. So, there are cool roofs, you would have heard about cool paints in the market, they all function in the same manner, that they have a high reflectivity and also high emissivity. So, usually what happens is that the denser material, a lot of building materials, they do not have very high emissivity, they absorb a lot of heat and then they gradually emit it later. What we want is that they should release all the heat that has been absorbed faster. Now, this is a technique that we are talking for warm climates and not for colder climates. So, the strategies will vary. For example, thermal mass, it will work for both the warm climates as well as cold climates, because in extremely cold climates the heat egress is taking place, the direction is reversed, that is it. So, thermal mass works in both the climates, cool roofs is only for warm climates. Now, next we are talking about courtyards. Courtyards are a common passive design feature. This is, we are talking it, this is pretty much a passive design feature which can be incorporated, but in today's times, since the land has become a precious commodity, we do not have as much of land, providing a courtyard has become extremely difficult. But if you look at the traditional architecture across the tropical belt throughout the world, you will see that the traditional houses, traditional buildings, they have courtyards. And how do they work? So, what happens is that during the daytime, the courtyard will receive a lot of sun and it will become warmer, and then it will start to, the air here will start to become lighter, and there will be, so not during the night, but we are talking about the hot summer day. So, there it is going to get lighter and it will rise up. Now, what it will do is that it will attract the air from the surrounding cooler areas, which will fill in for this negative pressure which is created here, and so there is a natural, it is an induced ventilation which is going to happen. Now, what we have to do, suppose we have thermal mass here, say a 2-storied building, and this is the courtyard that we are talking about. So, during the day, So, there is going to be hotter air which will rise up, and then we have to provide windows in such a manner that there is a draft of air which is created here, and the cooler air is drawn into this courtyard from the sides. Now, how do we ensure that there is cooler air here? So, we can actually have trees which will shade this space is cooler, or we could have water bodies, or we could have other mechanisms by which we can change the microclimate of this space from where the air is being drawn into. And to enhance the effect of this courtyard, what we can also have is we can have slightly harder surface here, paved surface here. So, it will heat up faster, and during the day it will release all that heat. And in the night time, what happens is that it will provide for the convective heating, that is during the winter nights, because this space has already gotten heated up. So, what we can allow this space will heat up the space here which is surrounding it. The courtyard also kind of acts as a balancer of activities. It provides as an active area in the comfortable times. So, early summer mornings, the winter days, the summer evenings. So, that is when the outdoor temperature is comfortable and the courtyard can be used. So, courtyard acts as a balancer of microclimate within the building. That is how it will work. The next we have wind towers. What do we do in wind towers is that there are openings at top from which, and we provide these openings in the direction of the wind. So, the wind is allowed to be caught by the wind tower. So, we know that wind is going to come from this side, and the wind will enter into this wind tower, and it will be allowed to settle down. And why will it settle down? Because this is hot air that is coming in. Again, wind tower is a feature that we are going to use for warmer climates. So, there is this thermal mass around. So, the wind towers, the walls of wind towers are going to be thicker, and this mass will absorb the heat from the air that is coming in from the top, and it will settle down. So, sometimes it will work like that. If we do not want to do that, and if we are providing the opening on the opposite side, so the wind only takes away the heat, in that case we will provide the first case we will provide the windows here in the bottom, so that the cooler air is entering into the rooms. In case we want to use the wind towers as exhausts, we will provide the ventilators at the top of these rooms, so that the hot air of this room is exhausted through the ventilator into the wind tower and then exhausted outside. So, wind towers can work both ways, and we have to construct them additionally as like taller chimneys, and they have to be taller than the building height. So, if it is a two-storied building, we have to make it at least another story high or even higher to make it effectively work. So, it can work in both ways. It can act as an exhaust of hot air, and then we can allow the cooler air, as we saw in case of courtyard, to be taken in from the other side, or we could use wind towers as a supplier of the cooler air. So, in a lot of architecture buildings in the desert areas, Middle East, we will see variations of these wind towers. So, sometimes they have the wind towers which are in this shape. So, this is the shape, this is the predominant wind direction in warmer months, and this wind tower and this entire facade is going to take the wind in, and this is a thick thermal mass that we would see, and this will absorb the heat from this air, and it will cool down and settle, and then we will supply it into the rooms. So, that is what we would see. Sometimes you would also see that there are openings on all sides. That is where, this is in cases where the wind direction keeps changing, and we are largely using the wind tower for exhaust. So, both ways. Then we have evaporative cooling. We know the fundamental of evaporative cooling, but then where to use and how to use. So, this is in a building in Bhopal where they have added water in the structure itself, and the air just passes through it and it gets cooled down due to this evaporative cooling process. We can enhance this. So, wind tower plus evaporative cooling will give us passive down draught cooling, and what we are doing here is that we have these taller chimneys, towers, and we have the sprays here. So, the spray is being done here, water spray. So, as the warmer air enters into this wind tower, so there is a spray of air and spray of water, and this air immediately cools down due to the evaporative cooling, and then as it settles down, then we allow it to enter into the spaces. Now, what are we doing here through these passive design strategies and advanced passive design strategies is that we are making the building comfortable and thereby reducing the requirement of energy for creating a comfortable environment inside the building. That is our prime aim when we are talking about all these passive design strategies. Again, this is a strategy for warm climate. Roof spray is very simple. So, now this particular passive design strategy requires some amount of energy to be put in. Even in the previous one, sometimes we may be adding exhausts here. So, mechanical exhausts can also be used to enhance the efficiency of this entire system. So, in that case they will be using some amount of energy. Of course, that can be through renewable sources, but it will consume some amount of energy in case we want to make it more effective. This one surely requires energy. So, what we are doing here is that we have fixed small sprays on top of the roof, and in between. So, it could be again checked that how frequently do we want to spray the roof, is it effective when we spray the roof when peak sun is there, when a lot of heat radiation is there, or it is better towards the evening or towards the night. So, when do we want to do it, but what we are really doing is we are spraying water on the roof. Roof is the element in a building which gets heated up the most because it receives direct sun, direct radiation. So, what we are doing here is that we are spraying the roof with water. It is taking up the heat and evaporating. So, that is, it is the simple process, but it takes some amount of energy which is much lesser than the energy which we would require to cool down the space indoors if this entire heat is going to get transferred inside. So, what we are primarily doing, all the heat that is absorbed by the roof is going to be taken out at a much smaller cost. That is what the roof spray would do. And the last strategy is earth air tunnel. It is very effective. So, what we are primarily doing is that we are allowing the air to be drawn inside a tunnel which is underground, which is under the earth at a depth at which the temperature of the ground remains constant throughout the year, which is the average annual temperature of the space we are in. So, it is at least 1.5 meter down, and this is a tunnel. So, what we are going to do is that, for example, if this is the building plan, this is here the building is, then we will have a tunnel. We will take the air in through some entry point, entry duct, and then we will allow the air to pass through this duct and then be supplied into the building. Now, by the time this hot air passes through this duct will take up all the heat, excessive heat, and it will do the reverse in cold climates also, because ground again remains at an average annual temperature. So, if it is extremely cool air here, when we are allowing it to move through this, it will take up the heat from the ground and it will come down when we are supplying it into the building directly, or maybe we are taking that air into an AHU, which this air becomes a pre-cooled or preheated air when we pass it through air tunnel. But again, in this particular strategy, there will be some amount of energy which will be consumed to make that air move, to push that air through the earth air tunnel. So, drawing it here and supplying it here is what will take energy. The exhaust fans, the pumps, that will take energy, and that is why we have kept it in the category of a of an advanced passive strategy. It is extremely effective, but it is also associated with some problems, for example, that of rodents. So, a lot of times these earth air tunnels, because they are underground, are infested with rodents, and then the moment we are supplying it here, that sometimes becomes a problem. There are mechanisms where we can solve them, and we have been able to solve them. There are some excellent examples of where earth air tunnels have been used. The similar concept has been used in the desert climate in Middle Eastern traditional buildings. There what they have done is that they draw the air to the level where there is an underground stream, and they allow the air to pass over the stream and be cooled again evaporatively, and then we take the cooler air from the lowest story of the building, and one story of the building will also be submerged, it will be underground. Now, this earth again is going to be at constant average annual temperature, and so the walls of this entire space is going to remain extremely comfortable throughout the year, warmer in winters and cooler in summers, but it is possible only in areas where the water table is considerably lower. If we are talking about warm humid areas or areas which have very high water table, then this will not work, because there will be a lot of moisture which will come in here. It works in desert climates, the arid and semi-arid climates, where the humidity in the atmosphere is significantly low, and that is where the building can be put underground, and also the air can be allowed to move over the water and then be supplied in the space. So, earth air tunnel again, as we have seen, will require in modern times some amount of energy to be supplied, but that amount of energy is much lesser in comparison to the energy that we would consume later if HVAC has to be installed inside the building to create a comfortable environment. So, with this I have kind of presented to you some advanced passive design strategies. There are a lot of other strategies which you would find literature about, and you can read about them, and they are all equally good and applicable. They will have their pros and cons. We have to read about all of them. Every strategy that I have presented here will come with its own advantages and disadvantages. We have to know that, we have to choose carefully, consciously, and see that what works best in the given context. But the whole idea of understanding these passive design strategies is that we create a comfortable environment right at the time when we are designing the building and constructing the building, and not think of the advanced strategies, the mechanical strategies as a first solution. Air conditioners are surely available, electricity is available, but the intent has to be to reduce the usage of this electricity as much as possible in the building through its design itself, and passive design strategies must be taken into account when we are designing. So, with this I will stop here for this lecture. Thank you very much for joining me. We will meet for the fourth lecture of this week tomorrow. Thank you. Bye-bye.